come to me saying, hey, for the last few questions, some questions kind of weird, how to do it. I said, well, give me time. We have still 2 lecture hours, and so here that is the way. From today and Wednesday, we're going to apply what we have learned on statics of the diffraction to the problems we call the static indeterminate problems. So that is the one case we're going to try. So now we're looking for is the applications. So here I give you the example of what would be the typical indeterminate problems in the beam. So here is the beam. And this beam, for example, is under a certain loading. So here, for simplicity, we assume omega equal to constant. For this case, I believe each of you should be able to do the calculation, to calculate the diffraction of this one based upon the technique we learned last time. And this is the determinant problems. Basically, here we can simply utilize the equilibrium equation that will be sufficient to solve for these problems. And on the other side, if we impose additional constraint, for example, for demonstration here, if here I impose additional constraint like this will completely change the nature of the problem. And I can tell you why. Look at here, at this clamp side, we would have the directions. For example, we expect direction V, and we expect direction moment M. And here we will respect the reaction force, that is P. And P is the vertical. Say, let me take away the P is, let me do this. So take the free body diagram. So this is the beam. And this is the force. On the free body diagram, we have V and M as a reaction at the left-hand side, and also the reaction at the right-hand side. So here, how many unknowns? We have 3 unknowns, which means M, V, and P. And how many equilibrium equations? 2. The force in what direction equal to 0, and the moment equilibrium to any point equal to 0. So here we have 3 unknowns and 2 available equilibrium equations. So here the number of the unknowns is greater than the number of the available equilibrium equations. So this one is defined as the static indeterminate problems. Okay, because by simply using static equilibrium, available static equilibrium equations, by simply applying the static equilibrium equation, that won't be sufficient. So we need additional information. So here we need is this. We need additional equations to solve for the unknowns. Okay, and what kind of the additional equations? And what kind of the additional equation? Actually, that will be additional compatibility equations. So here, for this example, the difference between the unknowns and available static equilibrium is 1. So we look for one additional compatibility equations. If we have, say, the additional, if the discrepancy number here is 2, then here we have to look for 2. Okay, so simply we have to make up the number of the total equation equal to the number of the total unknowns. So for this case, we have this one. So that is the definition of the static equilibrium equations. And how to solve for this kind of problem, and that is part of the homework. And here I introduce you right away the best method for solving this problem, and this method is based upon the superposition principle. And the textbook provides at least 2 methods. And now I'm going to show you is the best one, because that actually uses the minimum rigor, the minimum amount of the rigor in the calculations. Okay. So the method I'm going to show you is to how to solve for. So we can use the superposition principle. Solve this kind of problem. And here for these specific questions, the solution process is this. And here I use this as one example to demonstrate how to use the superposition principle. And then later on, for the remaining of the time today and Wednesday, we're going to do a lot of the few more examples to exercise this kind of problem. Okay. So the solution is this. Let me draw this one more time here. So we have these problems, and then for example here, assuming the length is equal to L, and our coordinate systems is X is in the horizontal directions, we put the origin at the left hand side and Y is here. The solution process is very similar to what we have learned in chapter 2. If you remember, we deal with the static equilibrium, the indeterminate problem in chapter 2. What we do is this. We choose, that is based upon the good faith exercise, which means based upon whatever you feel that is convenient based upon your logics, okay? And different logics have a different calculation, but you stick with your choice. And here I choose is this. For this example, we have identified, we have one more, we need one more additional compatibility equation, one more. So here, for this one, we choose to relax 1 degree of freedom. The degree of freedom, to relax the constraint. So here we have how many constraints? Here we have the constraint in y direction. We have constraint in the rotation here. We have constraint in the y direction. So here, for the 2 boundary conditions, that actually impose 3 constraints. Constraint 1 here, 1, 2, and 3. This constraint is to constrain the vertical displacement degree of freedom. V here constrain the vertical degree of freedom. The N here, that is to constrain the rotational degree of freedom. So here we have been constrained by 3 degree of freedom, but here we only have 2 equilibrium equations. So here we look for the one additional compatibility equation. The procedure is this. We need to identify one more. So here, starting with, you choose to relax the 1 degree of freedom in the constraint. So for example, here I pick this one. I'm going to deal with this one, okay? I'm going to remove this constraint by imposing the appropriate and equivalent description of the physical meaning, and let me to proceed. So for this case, if I choose to relax this one, you remove this one, and this removement, I'm not saying removement, I'm saying replacement. Replacement of such physical constraint is given by providing the corresponding reaction, okay? And we know that at this end, the constraint has been fixed. So that means y, and let me call this is a point A, this is a point B here. So y at B equal to 0. Again, replacement of the physical constraint is given by, one is we identify the certain unknown reaction, and also we know the vertical displacement has been constrained, so that means it is here. Okay? Okay, and that is the one here. But if you like, you can relax. Let me try to exercise the other option. So for example, if I want to try to relax the corresponding degree of freedom regarding this one, no, not regarding that one. Let me choose the easy one. This one. Okay. So the other option you might try is try to relax the corresponding constraint associated with this one. So here is the way. So this is a system. So here is the loading. And here is the constraint we have here. So right now, I want to relax this one. So basically, the degree of freedom is this constraint equivalent is replaced by such a degree of freedom has been replaced by the certain unknown m, and also by the rotation, which means theta equal to 0 here. And here, the simply we left is only constrained in the vertical, so here it simply become this one. Think about this one, okay? So think about this one. So probably you can accordingly to work on the relax the third degree of freedom here, replace the degree of freedom here, but that will be a little bit tedious, so I don't demonstrate this one. So this could be also do the work. But here for this illustration, let me work on this one. So now for this one, right now you can see, for this case, we can decompose into an equivalent, the summations of the subsystems. So here, plus okay. So here we have two kinds of the loading, and here we make assumption is the deflection will deform the beam, and the deformation will be still in his elastic domain, so there's no permanent deformation. So here the superposition principle should apply. So this is what we call the superposition principle. We simply decompose into the simpler format of the loading. And now for this case, and let me draw the deformation of the beam. So for this case, the deformation for this case will be something like this. And for this one, the deformation will be something like this. And let me call this is the y1 of x. And let me call this is the y2 of x. Okay. And so that means in total, the deformation of the system, let me draw it, the deformation of the system could be something like this. Okay, so for the original, let me call that is the y of x. So here the y by decompositions, this. That is y of x equal to y1 plus y2. Okay, so this is what we call the superposition. So for this one, right now we have utilized these informations. And I'm going to use the second information. The second information actually is what we call the compatibility equation. The compatibility equation basically is everything regarding the geometry. So this one. So from here, I want to impose is this. At point B, y of B of, at point B, that means at x equal to 0, at x equal to L, so that means YB. On the original system, we know that the B has been constrained in the vertical displacement, so that must be equal to 0, right? And that is the 0, that is from the given information. That is the boundary condition of the given one. And now we continue apply to this one, so this one will be equal to Y1 L plus Y2 L. Okay? So again, this one simply is to introduce at a specific location we simply apply to the original equation. And now to this point, what is this? What is this?
You should displacement or deflection of
Yes.
the first one.
Yeah, so basically this one, that is here, right? So that is Y1B, L. And for this one, this is this one, right? Y2, L. But I need numbers.
Here's the formula sheet.
Yes, so basically here I give you the handout, or from the textbook appendix D, this is a formula sheet. If you have that handout with you, take them out and tell me which case and what is the number there. Hi. I look at this, while you're looking for the information, I look at the statistics of the viewing the videos. I think the number just accumulating very slow and interesting. A few, I believe there's a group of the students in Malaysia. They follow this lecture notes.
In Malaysia? Or
Malaysia, Asian countries. But and I barely seen any reviewer except myself from Alaska. I'm so. What is this?
That was case 2.
Case 2?
Yeah, that's case 2.
And that's a case 2. And what is that? Can you read? Minus?
Minus M over 2EI. Or,
No,
oh, sorry,
not
I
case
was right below it. Omega.
L, 4,
over
AEI.
Yeah.
And the minus simply meaning downward. And how about for this one?
So then it's plus.
That is case, which case? This is a case 1, right?
Plus
And how much?
EL
Plus P times L cubed
over
3EI. So from here you can see this one is downward, so we take the negative. This one upward, we take positive. So from here we can solve for P. So therefore, 0 will be equal to omega 0 L force divided by AEI minus plus PL cubed 3EI. So therefore, from here we can solve for P first. The reaction is 3 omega L over 8. So once we solve for P, are we able to solve for V? So therefore, right now using the compatibility equations, we fix one unknown and leaving us 2 more unknowns. So right now we have P solved. So we haven't used the static equilibrium equations. So by the static equilibrium equation y equal to 0, so from here we can see from our drawing there V plus P equal to 0. So therefore V equal to minus P equal to minus 3 omega 0 L divided by A. So which means the V, assuming upward has a negative value there, so here the direction at here